Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. Wait, can you guys hear me?
Hello, doctor. Yes.
Okay, all right, good. Okay, so today will be so we are actually at the end of this semester already. So this is our last class. Okay, and today's will be a bit special because I'm going to offer maybe a lot of bonus marks today, and um, so following this according to these quotes, right? So means that a question is very important. Okay, so today's class, please focus, right? And at the end of the class, or maybe at the end of the example that I will explain, so to get a bonus mark, because I'm offering a bonus marks today, you should ask questions. Okay, so whoever asks questions, so maybe I'm going to pick maybe 3 to 5 questions. So those questions picked or chosen by me will get a bonus mark. Okay, so easy, right? It's not to answer a question, it's to ask questions. So just focus and hopefully you ask a question. So hopefully your question will be picked, right? So that you can get a bonus mark. Okay, so this is our actually our last topic, which is IIR filter design, and we have actually covered half part of it, all the conceptual, the theoretical parts. So we have covered that on how to design it, and today is actually just we're going to look at another example on how to design an IIR filter. Okay, and before that, it is good to recap a bit on how to design this IIR Butterworth filter. Okay, and if we look at this is actually a comparison between FIR and IIR, and because when we are designing filters, so we first actually try to find a filter spec, okay, the specification of the filter, and that specification is normally in a frequency domain. So we are finding what is the cutoff frequency, what is the transition bandwidth, what's supposed to be the ripple, those kind of things, right? And so we have seen this, and one of the things that we can see that the cutoff frequency for FIR is actually exactly at the center between omega p and omega s, and it is actually placed at a half magnitude of the spectrum. Okay, and but IIR filter, because this is actually following the Butterworth analog low pass filter. So the omega c, the cutoff frequency, is actually not exactly at the center of omega p and omega s. Instead, actually, this is a place on a half power. Okay, and that half power is actually 0.7071 magnitude. Right, so because this is from analog filter. Okay, this is actually a FIR filter. We designed it from scratch from ideal filter. So this is from analog filter. This is from ideal filters, and this is what we have. So okay, let's see what are the steps for this IIR filter before we go to the example. Okay, so of course the first step is so whatever we are designing a filter, the first step is supposed to be specifying the filter characteristic or specification. Okay, in this case, actually, we need to find what is we need to know what is the cutoff frequency, what is the filter order, those kind of thing, right? And then what is the second step? Second step is actually doing the for IR filter, because this is actually converting from analog filter to a discrete filter. So what we do is second step is to do a bilinear transformation. And what does that mean? So it is actually practically, we try to find what is the parameter C. Okay, so this is second step. So when it says that bilinear transformation, so theoretically it's that, conceptually we are doing that, but practically, so actually we are finding what is the parameter C. And finding parameter C can be done using this equation. So this is actually the general equation, so which is the capital omega prime. So that capital omega prime is actually referring to a normalized analog filter, the frequency of the normalized analog filter. Okay, so this is the keyword normalized. So because when we put it as a normalized analog filter, so we know that the cutoff frequencies, so this one, so if you look at what is the difference between this one and this one. So this is a general frequency, okay, angular frequency to be specific. But this is very specific. This is the angular frequency for at the cutoff frequency. Okay, so this is the cutoff frequency. So in terms of angular frequency. So that's why this is where we call it normal, because this cutoff frequency is set at equals to 1 always. Why we need to do that? Because it goes to the second, the third step. Because when we set it as a normalized analog filter, so we will have this standard equation. Because if the cutoff frequency is not equals to 1, you're not going to have this equation. You will have a different equation. Okay, we doesn't want that, because we want to have a standard equation. So that's if we have a standard equation, then it is easier for us to convert it into a digital filter. Okay, so then this is actually all those the first order, second order, third order. We can have a fourth order and so on. So this is a standard equation for a normalized filter where the cutoff frequency is equals to 1. And then what should we do is we're going to convert this, which is this is in S. So S is actually in Laplace transform, Laplace domain, the S domain using Laplace transform. Okay, so Laplace is for discrete for continuous time. And what we want is in discrete time, which is in Z. So this is in Z. So this is the digital filter. And to do that, so this is actually a shortcut method. So because originally what we do is we're going to replace every S with the relationship of the S and Z. Okay, too mathematical. So that's we simplify it a bit. Having a bit of shortcut, so that's we already know that whatever this equation is, it's supposed to be something like this. Okay, 1 over S plus 1. The digital filter is actually 1 plus Z minus 1 divided by D1 plus D2Z minus Z to the power of minus 1. Right, that's kind of a standard. So what we need to do is just how to convert this is just if it is a second order, you just pick this one and find what is a B11, B12, B13. And these are the equation on solving the B11, B12, B13. And for this one, D1 and D2, so you have a D1 and D2 here. Okay, and solving this, you need that C value. Okay, so where do you get this that C value? From second step. So because at the second step, actually you are finding the C value. Okay. All right, so that's basically the step. We just have basically 3 steps, but of course to implement it, so we need the 4th step. So which is we're going to transform or convert this HZ. HZ is called a system function. So we're going to convert this system function into difference equation. So why? Because a system function is in Z domain. To implement a filter, so we need to implement it in time domain. And implementing the filter in time domain, you need difference equation for IIR filter. Okay, if it is FIR filter, so you can have either difference equation or impulse response, because when you have an impulse response, you can do convolution. Okay, the normal convolution. So IR filter, you cannot do practically you cannot do the convolution because it will give you an infinite summation. So not possible, not practical. Okay, so that's why we are solving the difference equation instead of doing convolution. Okay, the original convolution. And of course, theoretically, difference equation is actually convolution. So, but it is a form of convolution which is a more practical form of doing convolution for an infinite summation. Okay, so if you do the normal convolution, you cannot do that. So only FIR can do it. Okay, all right. So let's go to the our example. So we have seen example 1. last Tuesday. Okay, let's see what is the example 1. So in example 1, so it's quite straightforward, because this is just, okay, design a second order butterworth filter. We already know what is the filter order, and it's already given what is the omega C, okay, which is 0.5 per radian. And then you just need to find C, and then convert this analog filter into a digital filter. So finally you get this one. This is the HZ, and then this is the Y, and after you convert the system function into difference equation. Okay, next we will look at example 5. Oops. Okay, in this example, so what is the question? Design an IIR butterworth filter that will attenuate frequency component. Okay, so this is actually some problem. So we need to understand the problem and then try to solve it. Okay, so that will attenuate frequency component omega equals to 0.5 pi, and omega equals to 0.59 pi. Okay, so it says that we need to design a filter so that it will attenuate or reduce or maybe remove this frequency component. So there are two frequency components, which is at 0.5 pi and 0.9 pi, okay, of the input signal xn. So shown below. So this is actually the signal. So this is a signal. So it has maybe several frequencies. Okay, but two of the frequencies is this one, 0.5 pi and 0.9 pi. Okay, and this frequency is in omega, angular frequency for discrete time signal. Okay, so hopefully do not confuse, because we have you already introduced to 5 types of frequency. Okay, because the original frequency is in hertz, which is a capital F. We denote it as a capital F. So that one is for continuous time. We have also angular frequency, capital omega. That one is also for continuous time. For discrete time, we have angular frequency, which is omega. And then we have a normalized frequency, which is denoted as small f, right? And last one is actually we have a frequency which we call a discrete frequency. We denote that as a k. Last time when we learn about DFT, okay, discrete Fourier transform. And here we are referring to omega. This is a small omega. So this is a discrete time angular frequency, right? Okay, so it says that also shown are the signals, magnitude, and phase spectrum. So this is the signal in time domain. So you also given this one. So this is the spectrum of the input signal. Okay, so remember, so because when we do a spectral analysis, so we can do spectral analysis on all 3 components, which is the input signal, the filter, and the output. So now we are looking at the spectrum of the input signal. Okay, so why we need to do a spectral analysis to input signal? Because we want to identify the unwanted signal. We want to identify what are actually our desired frequency. Okay, and because in these questions, it says that we want to attenuate the frequency component of omega equals to 0.5 pi and omega equals to 0.9 pi. So it means that these two frequency is the unwanted frequency. So we need to remove this. And looking at this spectrum, so basically we have 3 peaks, three significant peaks here. So the rest is actually just a side lobe. We call it a side lobe. So this is not why we have this, because our signal here, this is limited from 0 up to 100 only. So that's why you have this side lobe. When you will not have this side lobe, if you doesn't have this side lobe, means that you will have this signal from -infinity to infinity. Okay, so then you won't have that side lobe, right? But okay, but we know that we have at least 3 distinctive frequencies. Okay, so one is at, after we plot this, So we know that the first frequency is actually 0.1 pi, and then the second one is a 0.5 pi, and then the third one is a 0.9 pi. And we are actually trying to remove this one and this one. So these two. So this is the higher frequency, this is the lower frequency. So it means that to remove the higher frequencies, so we need a low pass filter. So we need a low pass filter. So it means that we need to design because this is an IIR filter design, so we need to design a low pass IIR filter design. Okay, IIR filter. So specifically Butterworth's filter in this point. All right, so just some notes. So the spectrum is based on 100 point DFT. This is actually the minimum because the signal is actually this is from 0 up to 99. So we have 100 point in time domain. Okay, so 100 samples. So that's why minimum for DFT is 100 point. So of course we can do a DFT for 1000 or 200 or 500, doesn't matter. Okay, but it needs to be at least 100. Right? And if you observe, this is just some facts. The magnitude here is actually equals to 100 A. This 100 is because you have 100 points in time domain. 100 A is the amplitude divided by 2. Right, so then we will know that at this frequency 0.1 pi. So because this signal is actually, if you decompose it, so you should have a three sinusoidal signal. Okay. Because we have a 3 here. So we have 3. So this signal is actually a combination of these 3. Right, so this is where the omega is equal to 0.1 pi. This is omega equals to 0.5 pi. And this is omega equals to 0.9 pi. Right, so you can see that the repetition is becomes higher and higher because the frequency becomes higher and higher. Right, so then if you want to know what is the amplitude here, the A of this 0.1 pi. So actually this is the relationship. So actually the magnitude in spectrum in frequency domain, so it's equals to 100 A divided by 2. So then you can have A. This is actually equals to that x omega times 2 divided by 100. Okay, so if this is a 50, then 50 times 2 is 100, then divide by 100, so it becomes 1. So actually this is equals to 1. Amplitude equals to 1. Okay, actually the amplitude is 1. And if the magnitude is lower, so this is actually 20. So if you replace this 20 times 2 is 40. 40 divided by 100 is 0.4. Okay, so actually this one is 0.4. And looking at this, so this is 30. So we can straight know that this is actually 0.6. Okay, that's the amplitude. So a different amplitude, so we'll give you a different magnitude. So this is why if you want to remove that, so we need to make sure that the magnitude goes to 0. So if the magnitude goes to 0, then amplitude goes to 0. Means that you remove that. You remove that frequency. If the amplitude is 0, so then it will be flat. So it means that we're not going to have that frequency anymore. So that's how filtering works. And if we are looking at this phase spectrum, so at all the frequencies 0.1 pi, 0.5 pi, 0.9 pi. So if you look at the phase, it is actually 0. Okay, so those are 0. So means that the phase, there's no delay. So everything is actually starting at this is cos without any phase. This is also cos without any phase. This is cos without any phase. Okay, so that's actually how do you analyze the input spectrum. Right, so we understand what is actually inside this signal. Okay, all right. So now we already understand what is the input signal, and we know that we want to remove two frequencies, and actually we are left with one frequency, which is 0.1 pi. So we need to preserve that. So we need to preserve that 0.1 pi. Okay, because the objective is actually just to remove the 0.5 pi and 0.9 pi. So this is actually a solution. Of course, you can have other solution. This is just an example of solution. So the solution can be many. Okay, the solution can be many. So this is just one of the solution. So below are the solution by applying a second order and ninth order IIR Butterworth filter. So we're going to try a second order and ninth order. So what will be the difference? And in this case, I'm using a cutoff frequency equals to 0.3 pi. Okay, here, this is 0.3 pi. So if we are looking at back at this, so we want to keep this one. We want to remove this one. We want to remove this one. So of course, logically, you're going to choose a cutoff frequency between this, between 0.1 and 0.5. Okay, so what I'm doing here is just I'm taking at center of it 0.3. So that's my point. That's how I decide. That's how I decide to take the omega c. Okay, of course you can do a 0.4. You can test that. You can use a 0.2. Okay, and maybe you can use 0.5. So or maybe just a bit here, 0.45. So that's because later you can see you can test some balance between the filter order, right? The filter order, the transition bandwidth, the ripple, all those kind of things. So after you choose the filter order and cutoff frequency, of course. So this is a combination of cutoff frequency and filter order. So but this is based on a second order Butterworth filter, omega c, which is the cutoff frequency, equals to 0.3 pi. So when I plot the filter, so this is what we get. Okay, so with n equals to 2, the transition bandwidth of the filter is actually quite wide, where the noise frequency of omega equals to 0.5 pi can only be reduced to 25% only. This one. So we can see that. So at 0.1 pi, so this is quite good because at 0.1 pi, this is the one that we want to preserve. So the magnitude is 0.9953. So it will not be 100% preserved, but it will just reduce a bit. Okay, maybe not that significant. So still good, still very good. 0.9 also very good because we want to remove this. So it is at a 0.0065. So very good. At 0.5, so this is this filter will not going to remove everything. So because this is somewhere at a 0.25. So this is why. So it will be reduced to 25%. So what is the original magnitude? The original magnitude is 20. So after filtering, so we are expecting that because our filter is at 0.5, the magnitude is 0.25. So quarter of this 20 is supposed to be somewhere at 5, right? Okay, before that, let's look at this. This is the phase. This is the phase, and this is actually what we call a non-linear phase. We did not cover a lot on this. Why? Because we can see that the line is not a straight line. Okay, if you have a straight line, that one is a linear phase, because a linear means a straight line. Okay, this is not a straight line, so that's why we call it a non-linear phase. So at 0.1 pi, so we will have some delay here because the phase is not zero. So at the output, we should see some delay. At 0.5 pi, we have a delay also because the phase is not 0. Same thing at 0.9, the phase is not 0. So we'll see some delay. Okay. And this is the pole zero plots, because this is a second order. And in this design, the Butterworth filter, all zeros will be here. Okay, so this is actually already fixed. So all of the zeros will be here at -1. So what will be the difference? The difference is the poles. So second order, we have 2 poles. And because we have only 2 poles, so it actually comes with as a conjugate pair. Okay, so this is a conjugate pair. All right, so the real value is the same. The imaginary value is actually having an opposite sign. And if you do this, all this step, if you do all this step, so this is actually the first thing, the omega c is a 0.3 pi. And then what will be the filter order? The filter order is a second order. So you need to find this C. Okay, you need to solve this one. You need to solve this one to find the C. This is already 1. We already know what is the value of this one, because this is a normalized frequency equals to 1. Then you're going to replace this one equals to 0.3 pi. Okay, then what is a C? C is just a 1 over, okay, this one, tangent 0.3 pi divided by 2. Then you will get a value of C. And after that, because you already know what is a C value, so second order, where is the second order? So this is the second order. So what you need to do is find what is the value of B11, B12, B13. And those B11 is actually equals to C squared. You already have your C here, plus A1C plus 1. What is the E value? The E value is 1.4142. Okay, because this is referring to the second order. So the second order, okay? Because if it is a third order, you need to refer to this one. So this is the second order. Then solve that, so you will get B11 and then B12, B13. And so please do that, okay? Please do that. So it is a very important. But I'm not going to do it in this example, because I'm going to show you more analysis on this example. And if you do that, you will get this value. So you'll get the value of B equals to this, and then the value of A equals to this. And again, as we have learned in a Tuesday class, this A0, make sure it is equals to 1. So if it is not equals to 1, so you need to factorize it. Okay, so make sure you factorize it so that this A0 is equals to 1. All right, so doing that, so actually we will have this system function 0.1311 on the rest and so on, and then divide by, this is the A0, okay, and this one. And then the fourth step is this one, which is convert this into difference equation. So this is your difference equation. Okay, then finish. Okay, so that's actually the filter. So that's the filter. So let's see. This is actually the output. So the one that we have done after this point, so actually now we have the difference equation. So to get the output, what will be the output? So we need to run this. We need to run this equation. What is the y0? It is a 0.1311 of x0. Okay, plus 0.2622x minus 1. And then plus 0.1311x minus 2. Because n is a 0, so you need to solve for minus 2. The same thing here, plus 0.7478y minus 1. And then minus 0.2722y minus 2. And of course, for n less than 0, okay, xn, so everything will be 0. Okay, we're going to assume that. We're going to assume that because we didn't start anything yet. So for y0, so actually you're going to have this value only. This one becomes 0, 0, 0, and 0. Okay, then after you have your x y0, then you can do the y1, because y1 is 0.1311x1 plus 0.2622x0. Okay, and then this one will be 0, this one will be 0, and you will have this one as 0.7476 y0. So you have your y0 here. Okay, x0 you have x0, y0 you have it. Okay, for y1, and this one will be 0. So you need to solve that one by one. So y0, if you have in this case, so we have 100 points, so you need to do it 100 times. So y0, y1, y2, y3 up to y99. Okay, of course, doing it on our computer, it will be very fast. So it will be very fast, right? And of course, we have learned some system realization, so it can be faster. So because based on a good realization, so we can reduce number of summation, we can reduce number of multiplication, and sometimes we can reduce number of memory. Okay, it can be faster. It can be very fast. Okay, so looking at this, so this is actually the third one, which is the output, because spectrum analysis is supposed to be on input, identifying the desired and unwanted signal, and then we have look at analysis on the filter. So this is the analysis on the filter. We already know that this filter is actually going to preserve the 0.1 pi, it will remove 0.9 pi, and it will reduce the 0.5 pi to 25%. Okay, and then we already know that you will have some delay here at 0.1, so you will have some delay because the phase is not 0. Another delay here at 0.5, another delay at 0.9. But at 0.9 is not that important, because at 0.9, so you won't have, it is almost removed. So the phase is actually not important anymore, because even the signal is not there. Okay, so this is where we can see that this is still almost 50, not equals to exactly 50, because it has been reduced a bit. Okay, and then this is very close to 5, because this is a quarter, 25% of the original. Original is a 20, magnitude is 20. And at 0.9, so we can see that it is almost removed. Okay, and the phase itself, so we can see that there is a phase. So this is an additional phase at 0.1, because the filter has a phase. Because originally the phase is 0, so now we have some phase here. So the same thing here, because phase magnitude, you do multiplication. Phase, you do summation, right? So this is a negative 0.14. Negative 0.14. So because originally the input signal doesn't have a phase, the phase is 0. 0 plus minus 0.14. So that's why you get minus 0.14 at 0.1 pi here. Okay, because it is a summation. So the same thing here. And this is the output in time domain. Okay, so this is the output in time domain. So what is this actually? So we have actually still have a two sinusoidal signal. So one is the 0.1 pi frequency, and then the other one is we still have a 0.5 pi frequency. Okay, but the 0.5 pi is because it's very low. The amplitude is low. So now we can see much of the 0.1 pi frequency. And then those maybe some jagged things is actually coming from the 0.5 pi. 0.9 actually is you cannot see the 0.9 pi anymore. Okay, because it's already almost reduced. And if we look at the sinusoidal signal with omega equals to 0.1 pi, so this is actually delayed by 1.4 samples. Because what is the delay? Delay is ND. ND is phase divided by the frequency. So the frequency that we are looking here is a 0.1 pi. 0.1 pi. So phase at 0.1 pi divide by the 0.1 pi. So you will get your ND. You will get your ND. So doing that, so you will get the delay equals to negative 1.4. So this is actually delayed. Originally, it is at 20. If you look back at the original signal, where's the peak? So this peak is at 20. This peak is at 10. Okay, now it's being delayed by 1.4 samples. So that's why we can see that in this example, so the peak here now is at 21.4 because originally it is at 20. So it's being delayed by 1.4 samples. So this is what happened if we have a phase in the filter. Okay, the signal is being delayed. Okay, so let's move on. We already seen second order. So let's see ninth order. So what will be the difference? So the difference between a second order and ninth order. Ninth order, we have it is actually a higher order. Okay, second order is quite low, and then we try to increase it a lot. So this is a ninth order. So what we have now is actually a very narrow transition bandwidth. Okay, so now the transition bandwidth is actually from here. So this is maybe somewhere at 0.2 something. Okay, and then before 0.5, it already becomes a stop band. Okay, so if you remember the previous one, the 0.2. So the transition bandwidth starts somewhere at 0.1. And then it ends somewhere at 0.9. So this is a very wide transition bandwidth. So when you increase the filter order, so the transition bandwidth becomes narrow. And actually, this is better to solve our problem here because we can see that at 0.1 pi, perfectly preserved. Okay, at 0.5 pi, so this is already 0, or maybe very, very close to 0. So actually, this is 0.0023, very close to 0. So good enough. Okay, good enough. And of course, at 0.9, this is already 0. And this is a phase. So the phase at 0.1 pi, so we have negative 0.57, okay, or maybe negative 0.58 if you round that. And then the phase at 0.5 and 0.9 is actually not important anymore because your magnitude has been removed. The signals have been removed, so this is actually not important because we're not going to see the 0.5 pi signal and the 0.9 pi signal at the outputs. Okay, that's what we expect. So we won't see these two anymore because it's already multiplied by 0. And this is the filter poles pole 0 plot. So because this is a ninth order, so you will see a zeros, a 9 zeros here at the same location at -1. Okay, and we will have a 9 poles. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1, 2, 3, 4. The first 4, 1, 2, 3, 4 is actually having a conjugate pair. So this is the first conjugate pair, the second conjugate pair, so the third and the fourth. Okay, because this is 9, so that's why we have 1 poles which doesn't have any conjugate pair because this is actually exactly on real axis. Okay, so there is no imaginary value on these poles. Okay, so that's our 9. And of course, I'm doing this using MATLAB because the ninth order, you will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 coefficient values, okay, for B and A. So of course in test and exam, so you won't be asked about the ninth order. So I'm doing this using MATLAB. Okay, but of course the same thing, the same process, you will do this, but of course in our notes, in the formula list, the ninth order is not listed. But of course, we can find that from somewhere, from some resources. So we can find what is the ninth order of this normalized frequency of the Butterworth filter. So we can find that. Okay, no problem actually. But of course, we're not going to do that in exam and test. So this is just for some analysis. Okay, so this is what we have. What I'm trying to show here is, this is actually one of the, I'm highlighting one of the term here. So let's see what it is. Generally, actually, we can, the HZ. Okay, actually, this is a general form of the HZ. So you have I from 0 up to 9 because this is the ninth order. So, and then it's just a summation of the filter coefficient to the Z of the minus I. Okay, the first one will be 0, then this is a Z to the power of minus 0 becomes 1. Okay, so that's why this is actually B0. B0 plus B1 Z minus 1 plus B2 Z minus 2 plus B3 Z minus 3 up to B9 Z to the power 9 minus 9. Okay, a summation. The same thing here, a summation. A0, which is equals to 1 plus A1 Z to the power of minus 1 up to A9 Z to the power of minus 9. So this is actually what we call a direct form realization. So this is the original. So this is the one that we already know. And actually when we do the this form, let's see. Okay, we have seen this. So this is the first order, the second order, the third order, the fourth order. So normally what you will have is this term. Everything is in a second order form. Fourth order, so actually we have a 2 second order form. Of course, this is a third order. You have a 1 second order term, and this is a one order, order 1 form, because 1 plus 2 becomes 3. This is second order. You will have 1 second order form, but fourth order you're going to have 2. And in our example here, because this is a ninth order, so you should have this one. This is a second order form. So you should have 4 of this second order form. Okay, so then actually what we can do is, and this is the ninth. This is the ninth order. Okay, so 4 of the second order, 4 times 2, 8, plus this one, 1. Or generally we can put it as a, this is one of the filter. We can, let's say, denote that as a HD. And then every second order form, so we can put it, let's say, a H1Z, H2Z, H3Z, H4Z. Okay, so, and actually this is, it has a name. So how we put it such this, so this is what we call a cascaded filter, right? So, and in final exam, we have this term, cascaded, right? So be sure that you know what is actually cascade. Cascade is actually you are multiplying every filter in this frequency domain or a Z domain. And what will it be in a time domain? So this is how it looks like. So Xn going through the HD and then goes to the H1, H2 up to H4, and then you get your outputs. So what is this? Because what is the properties? Multiplication in frequency domain is actually convolution in time domain. So this is actually your Xn convolve with HD, and then the outputs will be convolve with H1, and then the outputs will be convolve with H2, and then the output convolve with H3 again, and then the last one, the output here, convolve with H4, and then you will get your output. Okay, and then actually there's a reason why we do this. There's a reason why we do this. So we doesn't do like the whole thing as one filter, because doing that, so this is what we call a second order cascaded filter. So of a ninth order Butterworth filter. So because actually it has a low quantization error. We're not going to discuss this in detail. Okay, just you need to know that this arrangement, we call it cascaded. Okay, from one filter to another filter. So this is actually cascade. So there's a name, cascade. So that's in final exam. Then when you see the term a cascade, so now you know HD and H1 is cascaded is actually just HD and then go to H1. So you need to convolve this, right? So, but actually we do that because it has a low quantization error, because in discrete system, so we have this problem, quantization error. If we do everything the ninth order, so you will have a very big quantization error. So, but if you do every second order and then do another second order, do another second order, do another second order, so you will have a low quantization error there. And even in MATLAB, it has a function. So you can convert the original transfer function into this second order section. Okay, how to get this one by one? So actually we do this using, I did this using MATLAB. So there's a function, TF to SOS. So this is actually second order section, right? So just to let you know, okay? All right, so this is the output. So we can see that there's no magnitude for 0.5 and 0.9 anymore. So what we have is just a magnitude of 50 at 0.1. Okay, and then some phase at negative 0.58. So this is why now, so we can see some very smooth outputs, because this is mostly, this is actually the 0.1 pi. And it has been delayed. Originally, it's supposed to be at this peak, supposed to be at 20, but now it is at 25.8 because we have a phase. So that phase is negative 0.58 pi, and then you need to divide by 0.1 pi because we are looking at frequency 0.1 pi. And what you have is a negative 5.8 delay. So that's why the peak now is not at 20, the peak is at 25.8. Okay, so finish. So this is actually this example. As I mentioned last time, in final exam we have 4 questions. So the first and second question is actually more on time domain, Z and Z domain. Okay, Z transform. The third question will be heavily on DFT. The fourth question is actually on filter design, the FIR and IIR. So which is this example will be very, very important. Okay, the first example is very important. This example is very important. And I'm skipping a lot of examples. So you should look at those also so that you get more understanding. Okay, so now it's time, because I already finished. It's time for bonus mark. So, okay, let's see. I'm not sure if I missed out anything, but how we could determine the number of order for the filter, or why the example proper second order and ninth order for the filter? Right, good questions. Actually, that one can be considered as a question. Yes, how do you determine that? Is actually, if it is an IIR filter, so actually there is no a simple rules. There is no simple rules. Because there is no simple rules to know that n equals to 1, what is the transition bandwidth? Okay, n equals to 2, what is the transition bandwidth? N equals to 3, so what is the transition bandwidth? And this transition bandwidth can also be different when you change the cutoff frequency. Okay, so this is why when we are designing Butterworth's filter, so it's more like you need to plot the spectrum. So pick the n first, and then plot the spectrum, and then you should observe the transition bandwidth. Okay, so it's not like a FIR. FIR, it has a very clear formula on the transition bandwidth. So what is the transition bandwidth? So if we look at the FIR, so that's different for FIR. So FIR, so we have this equation. So this is a transition bandwidth. So we have a clear indication of what will be our transition bandwidth. Okay. So for rectangular, and then you choose your filter order, so you will get your transition bandwidth. So it is not for IIR, because even when you change the cutoff frequency, the transition bandwidth can be different for the same filter order. Okay, so we just know that if you have a higher filter order, so the transition bandwidth will be narrower. Okay, lower filter order, you will have a wider transition bandwidth. So just in this case, we are actually doing testing on two value of n, right? So okay, so that's why maybe it will be very tricky. That's why in exam we don't normally you just doesn't ask you to find out what is the transition bandwidth for IIR filter, because it's not, there's no a direct way of computing it. Okay, hopefully answering that. But of example 4, we could calculate the number of order. Yes, it's not direct. You need to have more information. If you have a very few information, you cannot do that. Unless in this example 4, this is actually a bit complicated. Because what we did is we specify what is the ripple. Okay, when you specify a ripple, let's go back to this one. This one, because a match is just if you have, let's say, how many values. So this is a ripple, this is another ripple on this one, and then you have a very fixed magnitude here on omega c. So maths is actually, if you have a 3 parameter, you should have 3 equation. And if you have that, so this is actually not by if you have a specific filter order, and then what will be the transition bandwidth. This is actually example 4 is reverse. If we need this transition bandwidth, so what will be the best filter order? Okay, the question is actually reverse. So it's not like filter order equals to 3. What will be the transition bandwidth? So that one is the one which is we're not sure. Okay, you need to run it, then you will have it. But this one is actually reverse. We specify this ripple, and then you have your omega c, and then you have your omega s. So actually you will have 2 equations according to omega c and omega s. So then you can do some solution on this one. Okay, and then do a lot of calculation, because now you have 2 equations. So 2 equation, 2 parameter, and then suddenly you can solve this. And estimating that the filter order should be at least 3. Okay, so at least 3. So yes, we can do that. Okay, so all right, so officially I'm giving Jason a 1 bonus mark. Very good question actually. So this is some kind of analysis that we need, right? Okay, let's see other. Is IIR filter linear? Just a simple question. Does cascading 2 second order filter create a fourth order filter? Okay, I'm going to answer Muresh first. Is IIR filter linear? Okay, that one is a very theoretical and conceptual questions. So is IIR filter linear? So the first thing is the one that we learn is actually LTI system, right? So what do you think? Is it linear or not linear? Even the system is called a linear time invariant. So of course, it is linear. So the system is linear. But what is the part that which is not linear? That one is the phase. So the phase is non-linear phase. Let's go back to this non-linear phase thing. Example 5 again. So it is a very specific. So this system is a non-linear phase. Non-linear phase means the shape of the phase is not linear, right? But the system is linear. So which one that we are referring that linear, that linear time invariant? The linear time invariant is when we do the filtering. So when we do the filtering, actually we are doing convolution. So convolution is a linear process. Okay, it is a linear and time invariant process. So it's a very unique because if everything becomes easier and simple, so these are everything that we learn because it becomes linear and time invariant. But this one is just because the shape is not linear. It's not a straight line. So then we call it a non-linear phase. So if the shape is a straight line, then we call it a linear phase. If the phase is just either 0 or pi, so then we call that a zero phase. Okay, because of the shape of the plot, not the filtering process itself. All right, so next, just a simple question. Does cascading a 2-second order filter create a fourth order filter? Yes, true. Another good question because that one is very important. Let's see our 9th order filter. Okay, now it's already 11. So those who have other class, so maybe you can leave the class. The rest, if you want to stick here, so you can stick, right? So if we look at this realization, so assuming this, let's say we have 2 second order, let's say only H1 and H2. The first one is second order. The second one is a second order. And the operation is multiplication. Okay. And of course, this one, second order. And then you have another second order. So this is because the operation is a multiplication, of course, you will get fourth order. Okay, because it's just a 2 multiplied by 2 because the operation is multiply. So, right? So the answer is yes. So you will get fourth order. Okay, now so we have Jason got a 1 bonus mark, and then Muresh got another 1 bonus mark, and then Umar, so you get 1 more bonus mark. So any other questions? I'm still opening. So we have a lot of attendance today, 26. Still opening for questions. Still opening for bonus mark. Any questions? So you can ask any questions. You can look, you can observe this, let's say, these plots and ask questions. Yes.
Doctor, just to clarify, we have cascading in the finals, right? But in the notes, it doesn't, at least in notes in e-learning, there's no cascading.
Yes, actually it is a term. So that's why actually I'm updating these notes. Okay, I'm updating these notes. Okay, so I'm going to check back e-learning. So if the note is not updated, I will upload the new one. Okay. So the term cascaded is actually in final exam. So because it's just a simple from one filter to another filter, we do convolution. Actually, it is when you put it in series. Okay, so actually this is in series. When you put a set of filter in series, so we call it cascaded. So it's just a term. Doctor, can you repeat what question is coming for final? Okay. that one you won't get a final exam, but I will answer that one. So we will have 4 questions. Okay, so we have 4 questions. You need to answer all 4 questions. Okay, you need to answer all 4 questions. So the first question is, I think it will focus on time domain operation. So mostly the early the early chapters. So on maybe testing causality, stability, those kind of thing, doing convolution. So those kind of thing. And then second question will be focusing on a Z transform. Okay. So we have a difference equation, we have impulse response, so we have a system function, we have poles and zeros, and those kind of things. Okay, we are focusing on Z transform. The third question will be focusing on DFT, the discrete Fourier transform. So this is where when we do a discrete Fourier transform, so what you need to understand is that DFT is actually referring to discrete frequency. So discrete frequency, so means that you need also to know the 5 types of frequency, because actually the other frequency is just you're going to convert that K into other frequencies. Right? So we have physical frequency in Hertz. So we have angular frequency, which is a capital omega for continuous time. And then we have normally we will write our frequency in a small omega. That one is for discrete time signal. And then lastly, we have that K. Okay. So that will be the third question. And then the fourth question is focusing on filtering. So filtering means we have 2 types of filter, so which is a FIR filter and IIR filter. Okay, so how to design it, and this kind of analysis, so which frequency remove which, so how many will be removed, so what maybe what is the difference between FIR, IIR, this kind of thing. Okay, so which one is better? So how do you analyze it on transition bandwidth, ripple, this kind of thing. Okay, so we need to understand those kind of terms because when it relates to filter design. All right, so those are the 4 questions in final exam.
This might be a bit far-fetched and I don't expect anything, but
Pardon?
is it possible to answer on an iPad?
I can clearly hear you.
Sorry, Doctor, is this open book? The test open book or closed
no,
book?
it's not open book. It's not open
Okay.
book. Okay, but you will be given all these formula lists. This is actually the exact formula list that you will have during your final exam. Okay, so that's why you need to look carefully. You need to be familiarized with this formula list, because in filter design, so in first table, so we have this impulse response for FIR windowing methods. So there's a one formula list here for FIR, and then this is a bilinear transformation. So there is a one formula here for IIR, and so we have a big table. This one, table 7 for FIR, and this is a one big table also for IIR. Okay, so that's why you need to get familiarized with this table. Right, so we have those properties. This is DTFT properties. So this is symmetry properties. Right, when you have an even signal, so you can use this simplified equation. So it doesn't need to memorize, but you can use this. So instead of using original formula, so maybe you can use this one. Okay, so maybe if you use original formula, then maybe you will use maybe you will use more time in solving it. But using this one, so maybe you save a lot of time. And this is the phase response formula. So we have how to compute phase for the first quadrant and fourth quadrant. So the second quadrant, the third quadrant. So we have everything here. And then I think even the Euler's formula is also here. So you doesn't need to memorize that. So, and this is also the frequency conversion. So we have those. So he doesn't need to memorize it. So it's just make sure you familiarize with this table. So we have a lot of tables. Actually, this is after back then. I think maybe 4 or 5 years back. We doesn't have this formula list because DSP is some kind of an open book exam and test. Okay, so but at some points we cannot do that. We cannot do an open book, so we list down all the formula, right? So that's why what it is. All right, so Nikesh, what is the necessity of approximation to design an IIR filter? Approximation. I'm not very clear of that question. Can you rephrase it? Or maybe can you speak at the mic? So what actually you mean by approximation? Approximation on which is there approximation on some value? Okay, so while waiting for Nikesh, any other questions? I'm still opening for a bonus mark. No one? No one wants bonus mark anymore? So today just Jason, Muresh, Umar. Let me write that first. So while you are thinking about, so I'm maybe I will give you for 5 more minutes, and then maybe we'll end this class. Nikesh, you might want to rephrase your questions so that you can get a bonus mark.
I'm just curious, why did this semester pole and zero got dropped from the syllabus? While
from the syllabus, actually we include on how to find poles and zeros, but the one that we skip is a relationship between poles and zeros and magnitude response. Okay, wait.
Yeah, I'm just curious, like, because did last semester batch learn about it, right? It's in their past year.
Yes, you're correct. So actually, the one that we skip is actually this one. This one. Okay, poles zeros. This is chapter 9. In chapter 9, so what is actually the relationship between poles and zeros with the magnitude response? So the main reason is actually we have a lot of break, and then we have a lot of holidays, and I just want to find some class replacement. Okay, maybe because that one is even quite difficult to do that. So then I skip that one. And another reason is because why I skip? Because why can I skip? Because there will be no question in the final exam in this part. Okay, because normally we did the final exam questions at the early of a semester. So we already know what will be in the final exam. Okay, so because even actually normally I already finish class at week 13. So, but this is one of the semester that I need to finish everything in week 14. Okay, because a lot of breaks and holiday. So that's why I'm skipping that part, because it will not be in final exam. Okay, so we are focusing on a different topics in the final exam. Okay, so right, so that's, but of course if you are interested to know, so of course you can contact me, and then we can discuss that. So I can show you what is actually the relationship between these two. Okay, between the poles and zeros, poles, zeros, and magnitude response. because basically, what is a Fourier transform? Fourier transform is a subset of Z domain. Okay, so it's just a one small part inside the Z domain. So that's why we have a relationship between pole zero and magnitude, right? So if you are interested, so please contact me. So then I can explain it to you. Nikesh is still nothing, Nikesh? So he doesn't want to rephrase that one because what is the necessity of frequency response approximation to design an IIR filter? Okay, I think what you mean is, okay, hopefully, I think that one is a very basic questions also. So what is actually the necessity of frequency response approximation to design an IIR filter? So hopefully I'm understanding right. Okay. So maybe your question is you're asking, so why do we need to look at a frequency domain in designing a filter? Okay, is that it? So that's why we start everything. Why we start everything? Finding the cutoff frequency, maybe a stop band H frequency, the pass band H frequency, the transition bandwidth, the ripple, which is everything is a spectrum. We are looking at spectrum to design a filter. So why is that? So hopefully that question is that one. So because again, a signal which have been proven by this Fourier. So it is a decomposition of a sinusoidal signal. So what is a sinusoidal signal? Sinusoidal signal is a signal with a unique frequency. So each sinusoidal signal has a one frequency. So what does it mean is we can rearrange our signal in frequency. Okay. So, and when we are doing filtering, because of that knowledge, so then people start doing when we want to process a signal, when we want to process a signal, actually it is better to look at a frequency, okay, rather than just looking at the time, because at the time domain it seems that not much that we can do. So but it seems that's a lot of things which is more make sense in frequency, like noise. So how do we identify noise? We identify the frequency. Okay, so and how different is an audio? So from one audio to another audio, so the difference is on the frequency. Okay, even images. If we look at image, okay, so how do we actually explain in maths images? So actually we can explain it in frequency. Okay, so then even in IIR, so that's why even the analog filter, the digital filter, so we are looking at this thing. So you have learned from even I think year one in circuit theory, so how the attenuation is done, so how a frequency is done, so what is the frequency from there. Okay, so that's why everything, so we're going to design and approximate everything from frequency. So then we're going to get our final product at time domain. Okay, so hopefully I'm answering that one. If not, so you can rephrase again. Okay, any question? More questions? Okay, last questions. Right, so actually that's why, as I mentioned, actually we already learned about frequency from year one, from your first year of studying. So actually you already been introduced to frequency, because of both signal is actually, it makes sense. So if we analyze it on frequency. Okay, so just actually this morning, even someone is actually asking me on how to do some analysis on a breathing sound. So of course, that one is also a sound. So that breathing sound, so how can we analyze that? So yes, we're going to analyze it on a frequency domain also. Okay, so I'm opening for last questions. So that's one of you still can get a one bonus mark. So far we have 4, including Nikesh. So including Nikesh, so you have 1 bonus mark. Okay, so is there any question? So it's supposed to be an easy bonus mark because it's not to answer a question. So it's just asking questions. I will answer it for you. Later, you should answer a question in final exam. Okay. Today, I'm answering the questions. So you just ask. Because that's how we learn, as we put it here, right? So you need to ask the right questions. So you need to have ability on how to ask questions. So if you're asking the right questions, you will normally you will get the right answer. Okay, so if you ask the wrong question, so maybe you will get a wrong answer. So even in research, we do that. We do that a lot. We ask a lot of questions because some questions, if you are asking, if you want to find some answer, maybe if you get the right questions, so it will answer it automatically. You will get your answer automatically if you get the right questions. Okay, no? Come on. I'm still opening it. One more because we have 4. Just another one.
Just if you pressure to ask.
That's question. You need to be brave enough to ask questions. I'm sure you have a lot of questions, but you need to be brave enough to ask questions.
Yeah. Sometimes I feel scared that I might sound stupid when asking a question.
Yes, actually, that's normal. The whole world, people will feel that.
Thank you, doctor. Thank you, doctor.
Okay.
Thank you, doctor. Last class, I need to leave. Sir.
So you have a question, Abdul Wahab?
No, I need to leave the class. I have other things to do.
Okay, I think maybe there's no more questions. Okay, but of course, if you have any question, you can always ask in WhatsApp group or PM to me. So whatever it is, just ask the questions. Okay, but of course, I'm not going to give you any bonus mark after this. But any question, just ask. All right. So that will be the end of this the class for this semester for this DSP. So hopefully everybody will do good in your final exam, and you still have one assignment, phase 2, part 3, which is the video presentation part. Okay. So after that, everything will be okay. Everything will be finished. So then just focus on your final exam. All right, so I think that's all. So good luck again. So assalamualaikum warahmatullahi wabarakatuh, and a good good morning to everybody. Okay, bye.
Thank you for your time, and see you.